Hello, I'm Dr. Tilaun Gutama. I'm a researcher at the University of Edinburgh. In the Titan project, our work focuses on designing resilient optical wireless communication, leveraging advanced signal processing techniques. In this video, I'm excited to share how our research is contributing to underwater optical wireless communication systems. Underwater communication is critical for unlocking the mysteries of our oceans, from environmental monitoring to enabling underwater robotics and exploration. Yet, traditional methods face significant limitations. Acoustic communication is inherently slow, and radio waves struggle to propagate through water. These limitations highlight the need for innovative alternative solutions, such as underwater optical wireless communication. However, the underwater environment poses unique challenges for light-based communication. Scattering, absorption, and turbulence degrade signal quality and reliability. This brings us to the core of our research. How can we overcome this challenge to achieve fast, reliable underwater communication? Our approach lies in digital signal processing to design a waveform that is used to carry data. That involves developing waveforms optimized specifically for the underwater optical channel, ensuring robust and reliable communication even under dynamic water conditions. We begin with subcarrier intensity modulation, a method where data is encoded in the phase or frequency of a signal rather than its amplitude. This avoids the limitation of amplitude modulation in turbulent underwater channels. Building on this, our primary focus is frequency shift chirp modulation. Chirp encodes data into a sinusoidal signal frequency linearly within its bandwidth, making it highly energy efficient and resilient to underwater channel impairments, such as turbulence. We started from simulations and moved on to hardware implementation using FPGA board. We developed a real-time system capable of transmitting and receiving data, bridging the gap between theoretical research and practical applications. Our experimental setup involves a commercially available laser diode as a transmitter and a photodiode as a receiver. To emulate underwater conditions, we use a water tank that can simulate still water as well as turbulence, which is induced by either temperature gradient using a heater or bubble flow generated by a wave-making machine. At the transmitter, information bits are encoded by the FPGA and used to modulate the LED, converting the digital signal into optical waves. These waves travel across the water tank, simulating a real-world underwater conditions. You can see in the optical wave propagation in the dark when the ambient light is turned off. At the receiver end, the photodiode converts the optical signal back into an electrical one, which is processed and decoded by the FPGA to recover the original data. For visualization, the same signal is split and fed into the oscilloscope here. This system has achieved reliable, error-free data transmission at rates of up to 1 megabits per second. Our next focus is on expanding our system to support multimedia data, including text, image, and video, and preparing for more extensive testing in various underwater conditions. The progress we've made so far highlights the potential of this technology. By tackling the challenges of underwater optical channel, we are paving the way for a new era of underwater communication. We would like to acknowledge the funding support provided by the Titan project, a consortium of 25 partners pioneering research in telecommunications for both UK and global societies and economies. Thank you for watching and for your interest in our research.